Hi. So, what are we doing here? We're studying vectors in three-dimensional space, right? So last time we talked about what vectors are and what we can do with them. So what can we do with vectors? We can take the sum of two vectors. We get another vector. This one. Let's see. Let me see if I can adjust it. Is that better? No? What is it about microphones in this class? By the way, I did find batteries after I finished last lecture. They were hidden in the cabinet. So don't make me do this. You don't want that. Let's see. Like this? Better? Yes. Okay. But tell me if you lose me. If I lose battery. So, all right. Yes, we can take the sum of two vectors, and it's a vector. Or we can multiply a vector by a number. That's a vector. But in addition, there are also more sophisticated operations we can do on vectors. For example, dot product. Now, dot product is a whole different deal because the input of a dot product is two different vectors, but the output is a number. The output is a number. And I explained last time that there are two ways to define the dot product of two vectors. The first way is geometric. We talk about the magnitudes of the two vectors and the cosine of the angle between them, which we call theta. So it's just the product of these three numbers. But there's also a second way, which is very convenient in calculations, which is defined in terms of the components of the vectors. And those components will be called x, y, and z. So I put index 1 for the first three components and index 2 for the components of the second vector. So the formula looks like this. Now we can play with these formulas, and we can derive useful information about vectors by using the fact that both formulas give us the same answer. Okay? For example, we can find the angle theta, the angle between the two vectors, by combining these two formulas. From the first formula, we learned that the cosine of this angle is equal to the dot product divided by the magnitudes. And now we use the second formula, so this is the first formula, and now we use the second one to write this in the second form, xy, x1, x2 plus y1, y2 plus z1, z2, divided by the lengths. But the lengths can also be found from the components. For example, the length of the first one is given by this expression, and likewise for the length of the second expression. So we can write this also very explicitly using the components, or coordinates, if you will. So you see, this is an unexpected formula in the following sense. You have two vectors, and which are given by these coordinates x1, x2, x1, y1, z1, and x2, y2, z2. When we just look at these coordinates, we don't know where exactly the vectors are. We have to plot them in space to really understand their relative position. So it looks like it would be very difficult to find out what the angle is between them. But in fact, there's a very explicit formula which uses nothing but the expression for a and b in terms of components. Right? So this formula only uses x1, y1, z1, which are the components of a, and x2, y2, and z2, which are the components of b. And a priori, there's no reason to believe that there would be such a formula, but we were able to derive it by combining two different definitions of the dot product. It's not like it's very simple, but it's not too complicated either. I mean, it involves some square roots and so on, but it is very explicit. So, for example, you can program it on your computer, and then every time so your programming computer would be like that black box, the dot product, for example. So you can program your computer to calculate the dot product, you get a number, but you can also program your computer to calculate the cosine of the angle by simply calculating this, and that's very simple, which can be done very quickly. So that's the power of this method that we're talking about. That using this method, we can learn a lot about the geometry of vectors, say, or other geometric objects, by using as input algebraic information, such as the components of this vectors with respect to the x, y, z coordinate system. One application of this is the following. There is a very special angle theta, for which the cosine is equal to 0. So cosine theta is equal to 0 if theta is equal to pi over 2. Or actually, not just one, but two different values, pi over 2 and negative pi over 2. Right? Right, so if you have an angle like this, the projection onto the x-plane, which is the cosine, is equal to 0. So in this case, the dot product formula tells us that the dot product is 0 in this case. So we can use it, you can use this formula to determine whether the vectors a and b are perpendicular to each other or not. When I say perpendicular, I mean that the angle between them is 90 degrees. But to say that the angle between them is 90 degrees, well, it means that they are either like this or like this. Right? It doesn't matter. In both cases, they're perpendicular. And in this case, a dot b is equal to 0. So if you're given two vectors, it's very easy to find out if they're perpendicular or not. You simply take the dot product given by this very simple formula, number 2, and you see whether if it's 0, they're perpendicular. If it's non-zero, they're not. So that's a useful application of all these formulas. There is one more operation that we will need for vectors, and that's called the cross product. Now, the terminology here is really not very, doesn't really make much, how should I say? It's not very imaginative in some ways. It's just that in the first case we denoted by dots, so we call it dot product. In the second case we denoted by cross, so it's called cross product. There's no other reason for calling them this way. It's just a tradition. So don't try to read too much into this terminology. It's just the way it is because of the kind of notation that historically people have gotten used to over the years. So the second operation is a cross product, and again I would like to think of it as a black box, which has certain input and certain output. Okay? But now the input will be the same as in the case of a dot product. The input will consist of two vectors. So the vector number 1 and vector number 2. But the output will be, instead of a number, in the case of a dot product, a vector itself. A vector as well. So the notation for this is A cross B. And again, there are two different definitions, just as in the case of a dot product. The first definition being geometric and the second definition being algebraic. So what's the first definition? The first definition, to explain the first definition, I have to draw a picture. So here I have two vectors A and B. And we should think that they don't necessarily lie on this plane, but in fact, there's some plane which might be sticking out. So I would like to imagine this piece of this plane, which is kind of floating somewhere. It's not inside the blackboard, but it's sticking out. In fact, I can use this blackboard to kind of illustrate it. So that's the kind of plane I'm talking about. Right? So in fact, I might use it. Never thought of that before. It's a very nice three-dimensional visual aid here. So it gives me a lot of flexibility. In fact, I can do all possible planes by turning it a little bit and then rotating. So no, really, I'm amused by this. Okay, it's nice to have good surprises. Okay, so here are the two vectors. Now I don't have to explain to you, okay, it's sticking out, because now you can see it. So here's A and here's B. Now, and that's the plane which contains them. So the result of the cross product of these two vectors is going to be a vector which will be perpendicular to this plane. Here I need a big stick, which I don't have, but I have a small stick. I have this. I have my pen. Okay, so it's going to be the eraser. Okay, thank you. So I'm doing really well in visual aids today. I'm very proud. So with your help, thank you. So to people watching, this is how it's done. This is a cross product of A and B. Now, so it's a vector which is perpendicular to this plane, which is good because I give you the direction of the vector. Actually, not exactly, because if I just say that it is perpendicular, there are two possibilities for it. It could go like this or it could go like this. But that's where I use the corkscrew rule, right? And the corkscrew rule tells me that it should. I use the corkscrew rule in the following way: that this vector, and this vector should form the oriented system, coordinate system. In other words, if I turn my corkscrew from A to B, it should move in the direction of this vector. So which means this is the correct position, not like this. Okay? So I explained to you what the direction of this vector is, but it's not enough. To define the vector, I have to tell you what the direction is, and I have to tell you what the magnitude is. So the magnitude of this vector is going to be the area of this parallelogram. So in words, the cross product is the vector perpendicular, and I will say the word oriented, where oriented means that A, B, and this vector satisfy the corkscrew rule or the right-hand rule, whatever you like. And this is a vector perpendicular. I can erase this now because I have a much better illustration. Perpendicular to the plane. I would say plane spanned by A and B. Spanned by A and B means a plane which contains both of them. It is in fact a unique plane. Unless, of course, these two vectors are proportional to each other. If the two vectors are proportional to each other, the answer is going to be a zero vector. So let me assume that they are not proportional to each other like this, so they are not pointing in the same direction. Then they do span a plane. There is a unique plane which contains them. Let me qualify this. There is a unique plane which contains them as soon as I specify a particular point. In other words, as soon as I say to which point I'm applying these two vectors. As I explained to you last time, a vector representation of a vector is not unique. In fact, I could parallel transform it. So I could apply it to a different point, which would simply mean moving this blackboard. I'm not going to do this. Now, it's perpendicular to the plane spanned by A and B. And by plane spanned by A and B, I mean what I just explained, of magnitude equal to the area of the parallelogram, which is drawn here. I'm not going to write it in words, just to save time. Okay? So what is this area? We can find it very easily because we know that the area of a parallelogram can be computed by dropping a perpendicular line like this. So this is 90 degrees. So let's call this h. And so this area is a, the length of A times h. Right? I have to be careful not to shift it. You know what I mean. A times h. But h, in turn, is the length of B times the sine of this angle right here, which I call again theta because that's the angle between A and B, right? Because you got here a triangle for which this is 90 degrees. So you can find this side by taking this side, which is the length of B, and multiplying by the sine of this angle. So h is this, and therefore the length of A cross B is the length of A times h, which is length of A times the length of B times the sine of this angle. So to repeat, the cross product of two vectors is a vector perpendicular to the plane spanned by these two vectors, which satisfies the orientation rule with respect to those two vectors, and whose length is equal to the length of A, length of B, times the sine of the angle between them. This is the analog of the first definition of the dot product, which also involves nothing but the length and the cosine of the angle. In this case, there's a little more because I also specify a particular direction, which is determined by the plane. Now, what about the second definition? In the second definition, I'm only allowed to use the components x1, y1, z1 of the first vector, and x2, y2, and z2 of the second vector. Right? So a priori, it's not clear what the formula should be. So I'll just give you the answer. And then it's an interesting problem, which you can read about in the book, to see that indeed the two definitions are equivalent. Last time, I explained to you how to show that one definition implies the other. I did not explain how the first implies the second, which you can also read in the book. So the second definition is the following. It involves a new piece of notation. which is called the determinant. The determinant is given by a certain formula. You apply the determinant to this table, or 3 by 3 table of symbols, which you can multiply and add to each other, as is the case here. And specifically, the formula, in this case, more concretely, the formula is the following. There's a simple rule how to calculate it. And the rule is that you have to go along the first row, so you have I, then you have j, and then you have k. So the formula will have 3 terms, one corresponding to I, one corresponding to j, and one corresponding to k. The term corresponding to I is obtained as follows. You simply cross the colon in the row where you have I. So what remains is this 2 by 2 square. And in this 2 by 2 square, you take the product along this diagonal minus the product along this diagonal. So this minus this. In other words, what you have is I multiplied by y1 z2 minus z1 y2. This is the first term. For the second term, we take j, and to get the corresponding term, we cross out the row and the colon where j is positioned. So what you end up with again is a 2 by 2 square. You can put them next to each other, so you get x1, z1, x2, and z2, and you take this diagonal product minus this diagonal product. So the result is j times x1, z2 minus z1, x2. And finally, you do the same to k, so the result is this square. Then you get x1, y2 minus y1, x2. And there's one more thing you have to remember. You have to remember to alternate the signs. So you put plus here, minus here, and plus here. Well, this you don't have to put because it's the first sign equal, meaning that I'm continuing that formula. Okay? So very explicit, something you have to play with it to memorize. Not too difficult. Yes? What about? Yeah, you can use, question is what about some other rule which I put here. But you can use whatever rule you like, as long as you get the right answer. It's fine. I'm sure some people can just look at it and tell you the answer. I think it's much easier than doing a Rubik's Cube, to be honest. Some people can do it in like 20 seconds. So, not me. All right. So I'm sure each of you will have their own way to calculate this. I just told you mine. Which one? It's not mine, of course, but the one I use, and which I think most people use. Okay. So that's the cross product. And so again, you have two different definitions. One is geometric, it's about the vectors and their positions and the angle between them, and the lengths and so on, geometric characteristics. And the second one is algebraic in terms of just the components of these vectors. And so what it means is that you can also apply this to calculate various things. For example, you can calculate this way the area of the parallelogram, which is spanned by these two vectors, because the area of the parallelogram is just the magnitude of this vector. Right? So we can use it to compute the area of the parallelogram by simply taking the magnitude of this vector, which is to say, taking the square of this coordinate plus the square of this coordinate plus the square of this coordinate and taking the square root of the result. Let's do some calculation. Let's say example, find area of the parallelogram. Let me just, to save time, write a parallelogram like this, spanned by the vectors A, which is equal to 1, 2, 3, and B, which is equal to -2, 3, and 1. Okay, just random numbers. Okay, very easy. So first of all, we calculate the cross product between these two vectors by using this formula. So we put I, j, k, 1, 2, 3, -2, 3, 1. It would be embarrassing if the answer is 0. So they will actually be parallel. Although that would be a good illustration of that case. So, so I is equal to, in front of I, we have this one. So it's 2 minus 9, right? And then you have to put minus. Remember, there's a minus. Maybe I should emphasize it. So there's a minus here in the middle. So put a minus. Then you have j, so you have 1 plus 6. Okay? And finally, you have, in front of k, you have this, 3 plus 4. So that's minus 7, -7i, minus 7j, plus 7k. Okay? So that's the cross product. And you want to calculate the area. To calculate the area, I have to take the magnitude of this vector. Please check my calculations because who knows. So now the magnitude is just the square root of the sum of squares, which is 7 squared plus 7 squared